First, let's take a look at an electromagnetic wave and what it's composed of. It's a transverse wave that consists of oscillating electric and magnetic fields at right angles to each other. So let's take a look here. This is the electric field represented by this dashed yellow line, and this is the magnetic field represented by this dashed blue line. And notice that the direction of the EM wave is in this direction. So this is at a right angle here. Alright, this wave right here is at a right angle there. But this one is also at a right angle, but drawn into the page. Now what we'll notice is that they're both at right angles, so this is indeed a transverse wave, as we had mentioned in the last section. Some types of electromagnetic waves. First, we have our radio waves, and our radio waves have the highest wavelength out of all these waves in the EM spectrum. Take a look. Lowest wavelengths are down here, on the order of nanometers. Highest wavelength are greater than 30 centimeters, lambda. And radio waves traditionally are for, radios and old TVs with antennas. And notice that these, although they have the largest wavelength, they have the smallest frequency out of all the possible EM waves. We'll see that the gamma rays have the highest frequency here. Next are microwaves, and those range from 30 centimeters up to, or down to rather, 1 millimeter, and their frequency ranges from a small value of 1 times 10 to the 9 to a larger value of 3 times 10 to the 11. And microwaves are traditionally used for like radar, aircrafts, some research for scientific purposes on an atomic level, and then obviously for microwave ovens. Infrared waves, notice infrared waves here. Next, they have a wavelength between 1 millimeter and 700 nanometers. So this is our maximum wavelength. This is the smallest. We're on the scale of nanometers already here. And the frequencies range from 3 times 10 to the 11 to 4 times 10 to the 14 hertz. And IR waves are traditionally used for things like thermal imagery, for infrared cameras, and then also for, physical therapy. The visible spectrum ranges from red all the way to violet. Red being the largest wavelength, violet being the smallest wavelength, but if we look at the frequencies again, they're opposite. Okay, because again, wavelength and frequency are inversely related to one another. The smallest wavelength, smallest frequency here, and then the largest frequency in the end where it's violet. And notice that the visible light spectrum is made up of red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. And what we'll notice is that the red on the far left here, the red has the smallest frequency and the violet has the highest frequency. And that's why these waves that have a smaller frequency even further than red are called infrared, meaning below red for frequency. And above the violet rays that we're seeing on the violet end of the visible spectrum, we have ultraviolet or above violet. And these frequencies are higher than that of the violet spectrum. Now, think of something like a black light. A black light would fall between violet and ultraviolet. Let's take a look. We know what visible light is used for, obviously, okay? Visible light photography, microscopes, astronomy, many other things, obviously. Next are the UV rays, and UV rays have a range of wavelengths, the largest being 400 nanometers, the smallest being 60 nanometers, and then the smallest frequency of 7 times 10 to the 14, largest of 5 times 10 to the 15. Some applications of UV rays are to sterilize medical instruments. So when a doctor works on you or a dentist, the materials or the tools they're using are sterilized, not only clean, but sterilized using UV rays. Also to identify fluorescent minerals, sometimes used for forensic science to detect things like drugs. Okay, UV rays could be used to see if there's any fluorescence given off by a certain drug to indicate what it is, or maybe used for different minerals and rocks in the earth when trying to mine in certain areas. Next are the X-rays, and the X-rays again have a wavelength that's going to be a little smaller than this. Notice our wavelengths, largest was up here, and we're getting smaller as we go down. So that ranges from 60 nanometers at the highest to 10 to the negative 4 nanometers at the smallest. And X-rays are traditionally used for examining bones, teeth, and organs, and then it's also used to treat certain types of cancer. And you'll notice that X-rays go up to a frequency of the 21st, or on the order of 10 to the 21st, and gamma rays start down at 18, so there's a little overlapping in these bands here. The last thing, again, are gamma rays. And most people are familiar with the fact that treatment of types of cancer uses gamma rays. But I find it really interesting to see that it's used for food irradiation, to get radiation out of food, and also to examine thick materials for structural flaws. So think about like a column that's holding up a building. How are you able to see if there's a crack in the center of that cylindrical column? So this is just another application of using gamma rays. Now what we should notice is that this is on a spectrum, which means it ranges. So at the lowest frequency we have our radio waves, then we have our microwaves, and after that we have the infrared waves, then we have the visible light spectrum, then ultraviolet spectrum, then we have the X-ray spectrum, and then we have gamma rays. And these widths are not drawn to scale, and you'll notice that the visible light spectrum is very small in its range, ranging in frequency starting at 4.3 times 10 to the 14, ending at 7.5 times 10 to the 14. So these bands each have different actual widths to them. They're not going to be considered to be equal in distance. Next, the speed of light. The speed of light is a universal constant, and it's the maximum speed at which all energy, matter, and information in the universe can actually travel. And this is the speed at which massless particles, including EM waves, they travel in a vacuum. The fact that this is finite is pretty unbelievable to think about, meaning that nothing can actually surpass the speed of light. Now, some quick facts for you. It would only take something traveling at the speed of light approximately 0.013 seconds to get across the U.S. So we're talking about 1/100th of a second to get across the U.S., which makes sense because if you think about how do you instant message and chat and video message with people across the world, well, electromagnetic waves that carry those signals travel at such a high speed that it only takes this much time to get across the U.S. Okay, so imagine now you're in the U.S. and you send it up to a satellite, and the satellite brings it back down somewhere in like China or another country. Well, it has to travel this distance and this distance, so maybe it's a little further. So maybe it takes like, 0.05 seconds, triple that time or triple that value across the U.S. because maybe this distance traveled is 3 times as far now using a satellite as a router. Another fun fact, it only takes about 8 minutes for light to travel from the sun all the way to the earth. From the sun all the way to the earth. And if we think about it, that means that the light that we're seeing from the sun is actually 8 minutes old. So if one day the sun were to explode, we wouldn't feel that radiation or see the difference or see the sun go out in a sense until 8 minutes after it actually happened. Example 1 says the FM radio band extends from 87.5 to 108 megahertz. What are the longest and shortest wavelengths in this frequency range? Well, we know our formula is V equals omega lambda, but V in this case would be velocity. Well, that's a constant. Right? It's the speed of electromagnetic waves. So it's C, the constant, equals omega lambda now. And now if we're taking a look, we're trying to figure out the longest and shortest wavelengths. Let's solve for lambda. Becomes C over omega. Now I have 2 conditions. This is my first omega, this is my second omega. And these values we have to consider are the fact that this is 87.5 times 10 to the 6 hertz. And the second one is 108 times 10 to the 6 hertz. Again, because of this mega. Mega means times 10 to the 6. So this is the minimum frequency, and this is the maximum frequency we're looking at in the range. Well, if you realize something, that the wavelength and the frequency are inversely related, if I plug in the minimum frequency here, I'm going to get the maximum, or the longest, wavelength. If I plug in the maximum frequency, I'm going to get the shortest wavelength. So let's go ahead and take a look at these 2 scenarios now. So we can do this twice. Lambda max, again, means use the smallest wavelength, frequency right here. So that's going to be 3 times 10 to the 8, again, the speed of any EM wave, meters per second, over 87.5 times 10 to the 6 hertz. And remember that hertz is really 1 over second. So I'm going to put 1 over second here to get rid of hertz, and notice that seconds cancel, leaving behind meters, which makes sense because I'm looking for wavelength. And if I divide these 2 quantities for the maximum wavelength we're going to get is going to be 3.43 meters. Now if I want to find the minimum wavelength of the FM spectrum, I still take, again, the speed of EM waves, 3 times 10 to the 8 meters per second, over now, though, the maximum possible frequency here, which is 108, or station 108, times 10 to the 6, because it's in mega. Again, the hertz cancel with the 1/2, because that's really, hertz cancel with this second here, because hertz is really 1/2, leaving behind meters. This gives me a value of 2.78 meters. So the minimum wavelength of the FM spectrum is 2.78 meters, and the maximum is 3.43 meters. The final thing to think about is the fact that brightness of light is a function of how far you are from the light source. And this is really important because astronomers use this to measure distance to stars, actually. And we know that if you want to read something, right, you turn on a lamp, but if it's closer, it's brighter, it seems at least. And the further it goes, the less bright it gets over a larger area. And what we can really say is that the apparent brightness is proportional to the actual brightness over the distance squared. Now there's a more complex formula that involves using the luminosity as well, but this is the general gist of what astronomers think about, because the actual brightness over the distance squared is what you are really seeing. First, we'll start with our definition of reflection, which is when an electromagnetic wave is redirected outwardly at the surface of a material. And you've seen this before with light. If you've ever seen light shine off the surface of water when it reflects off, or when you see a reflection in a mirror. But let's take a look at two different types of reflection. First, diffuse, and then specular. Diffuse reflection is when a surface is rough and it comes off at random angles. Notice that these are going off in scattered directions. So the light rays come in parallel, and then they come off at different angles. Whereas specular surfaces are smooth surfaces that are reflected in one direction or in the same direction. So these come in parallel, and these all go off parallel as well. For specular, think of a mirror. For diffuse, think of like concrete, and how light does reflect off concrete, but it comes off at different angles. It's a rough surface. Next, let's take a look at the law of reflection. The law of reflection tells us that the angle of incidence, the incoming angle, is equal to the angle of reflection, the outgoing angle, for smooth surfaces. And here's your example right here. If we look at this one and we draw our normal, we can see that the angle of incidence is equal to the angle of reflection here. Okay, equal to one another. So the angle of incidence is denoted as theta. The angle of reflection is denoted as theta prime. And notice that these angles are measured from the normal. If a light had been directed from straight above along the line of the normal, it would go straight back upward in this direction. Next, let's take a look at the visible spectrum, and we can remember Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And sometimes books, especially your textbook, leaves out indigo, which is really just the shade between the blue and the violet colors. And now what we should notice, though, is that color is really the result of a surface that absorbs parts of the visible spectrum and reflects only one part, or a combination of parts that give only one color. So specifically for green, all these colors are absorbed except for green. Now sometimes when you see shades, that's because certain parts are absorbed and then there's a combination that is reflected. What we should also notice is that the result of all the colors being reflected is the color white. And when all the colors are absorbed by a certain material, the pigment that you're seeing there is black. Now that's the reason why in the summertime, when you go to, say, the beach, or you're out somewhere where there's a lot of sun, you'll wear a white t-shirt so it reflects all the colors of the spectrum, as opposed to a black t-shirt which absorbs all the colors so it doesn't heat you up as fast. Now the primary colors. Now here we're looking at the primary colors of visible light. We're not looking at primary pigment colors, which have to do with art. So we're looking at the three colors, red, blue, and green, that can be added together in different proportions to create any of the other colors of the spectrum. And what you'll notice is that when the overlapping of all three of these colors occur, we get white light in the middle there. When these two colors overlap, we get yellow light. Now, one thing to note and to see is that these are the same three types of receptors that humans have in their eyes. Those are called cone cells. The cone cells can read or can interpret the different colors. And it's also seen in TV screens or like any sort of monitor, where the pixels, really what they are, is one of the three primary colors at different brightness levels. So every single individual pixel is just either red, green, or blue. The combination of all those pixels at once is what you're seeing, and those pixels are constantly changing by rows, but the change occurs so quick that it seems smooth on the TV, even though those pixels are actually changing colors using transistors.